Dear students, let us start with remark. Least upper bound of LF sigma is always less than or equal to greatest lower bound of UF sigma. Why this is? Because LF sigma is less than or equal to UF sigma. If you take least upper bound of your LF sigma, it is less than or equal to greatest lower bound of UF sigma. Where least upper bound and greatest lower bound are taken over all subdivisions sigma of closed interval A. Okay. In this video, we are going to study most important topic: upper integrals and lower integrals. Upper integrals and lower integrals. These are the most important topic of this chapter. Let capital F be bounded function. Let capital F be bounded function on the closed bounded interval AB. Then upper integral of F over closed interval AB is denoted by integration from A to B bar F, or integration from A to B bar F of x dx. Sorry, here F is capital and is defined as integration from A to B bar F of x dx is equals to greatest lower bound of UF sigma, where greatest lower bound is taken over all subdivisions of closed interval AB. Okay. Similarly, lower integral of F over closed interval AB is denoted by integration from A bar to B F, or integration from A bar to B F of x dx, and is defined as integration from A bar to B F of x dx is equals to least upper bound of UF sigma. Least upper bound of UF sigma. See here, F be bounded function on the closed bounded interval A. Then upper integral of F, here F is capital, over closed interval AB is denoted by integration from A to B bar. For upper integral, we give bar on upper limit, or integration from A to B bar F of x dx. It is defined as integration from a to b bar f of x dx is equals to greatest lower bound of uf sigma. Similarly, lower integral of f over closed interval ab is denoted by integration from a to b, integration from a bar to b. In case of lower integral, we give bar on lower integral. Okay, it is defined as least upper bound of uf sigma. Okay, where least upper bound is taken over for all subdivisions or sigma of closed interval AB. Okay. Now this is the definition of upper integral and lower integral. Okay. Now we will see definition of Riemann integral. Okay. If f is a bounded function, on closed and bounded interval AB, we say that f is Riemann integrable on closed interval AB if integration from a to b f is equals to integration from a bar to b f. Okay. In this case we write integration from here a to b bar. A to b is equals to integration from a bar to b f is equals to integration from a to b bar f. Okay. We denote it by f is belongs to Riemann integrable. F is Riemann integrable on closed interval AB, where R of closed interval AB is class of all functions f which are Riemann integrable on closed interval AB. Riemann integrable on closed interval. Okay. Let us take next theorem. This theorem is called necessary and sufficient condition for function is Riemann integrable. That theorem is the function let f be small f be a bounded function on closed and bounded interval AB, then f is Riemann integrable on closed interval AB if and only if for each epsilon greater than 0, there exists a subdivision sigma of closed interval AB such that UF sigma is strictly less than LF, take here small f, LF sigma plus epsilon. Okay, what is clear? F be a bounded function of closed and bounded interval AB, then F is Riemann integrable on closed interval AB if and only if for each epsilon greater than 0 there exists a subdivision sigma of closed interval AB such that UF sigma is strictly less than LF sigma plus epsilon. Okay. Now see next topic, existence of the Riemann integral. Existence of the Riemann integral. Okay. Necessary and sufficient condition for the existence of the Riemann integrable is, actually this is a theorem. Which theorem is called necessary and sufficient condition for the existence of the Riemann integral. Let capital F be the bounded function. Let capital F be the bounded function on the closed bounded interval AB, then F is Riemann integral. That is, in bracket we can write F is Riemann integrable. Okay. If and only if F is continuous at almost every point in closed interval AB. Okay. F be the bounded function on closed bounded interval AB, then F is Riemann integrable if and only if F is continuous at almost every point in closed interval AB. What is the necessary and sufficient condition for F is Riemann integrable? It is F is Riemann integrable on closed interval AB if and only if F is continuous at almost every point in closed interval AB. Continuous at almost every point means it will be not continuous at every point in closed interval AB. Students, here note that continuous implies continuous almost everywhere. Means always remember that every continuous function is continuous almost everywhere, but converse need not be true. Means continuous almost everywhere function everywhere does not imply continuous. Okay. Next topic is properties of Riemann integral. Properties of Riemann integrals. Properties of Riemann integrals. Okay. Actually, these all are theorem. Theorem 1. If F is Riemann integrable on closed interval AB and A is strictly less than C is strictly less than B, then f is Riemann integrable on closed interval AC and f is Riemann integrable on closed interval CB, and integration from A to B f is equals to integration from A to CF plus integration from C to B f. This is the first property. What is that? If f is Riemann integrable on closed interval AB, A is strictly less than, C is strictly less than B, then f is Riemann integrable on closed interval AC and f is Riemann integrable on closed interval CB, and integration from A to B f is equals to integration from A to C plus integration from B to C f. This is the first property. Now second, theorem 2, which is the second property. If f is Riemann integrable, if f is Riemann integrable on closed interval AB and lambda is any real number, then lambda into f it belongs to Riemann integrable, means lambda f is Riemann integrable on closed interval AB, and integration from A to B lambda into f is equals to lambda integration from A to B f. Okay, this is second property. This is very simple. F is Riemann integrable on closed interval AB and lambda is any real number, then lambda into f is Riemann integrable on closed interval AB, and integration from A to B lambda f is equals to lambda into integration from A to B f. Okay. Third is theorem 3. If f is Riemann integrable on closed interval AB and g is Riemann integrable on closed interval AB, then f plus g is Riemann integrable on closed interval AB, and integration from A to B f plus g is equals to integration from A to B f plus integration from A to B g. This is the third property. What is that? F is Riemann integrable on closed interval AB and g is Riemann integrable on closed interval AB, then their addition must be Riemann integrable on closed interval AB, and integration from A to B f plus g is equals to integration from A to B f plus integration from A to B g. Okay, this is the third property. Okay. Now let us see one lemma. Lemma is, if f is Riemann integrable on closed interval AB and if f of x is greater than or equal to 0 almost everywhere in closed interval AB, then integration from A to B f of, if you take here small f, then again here take small f, here is small f of x which is greater than or equal to 0. Proof. See here, if f is Riemann integrable on closed interval AB, f of x is greater than or equal to 0 almost everywhere in closed interval AB, then we have to show that integration from A to B f of x is greater than or equal to 0. Okay. Since what we have given, f is Riemann integral on closed interval AB. Take here small one. Therefore, what happened? By definition of Riemann integral, upper integral is equals to lower integral. Integration from a to b bar f is equals to integration from a bar to b f, which is equals to integration from a to b f. Call this equation 1. Now let sigma be any subdivision. Let sigma be any subdivision of closed interval AB, and let I1, I2 and so on up to Ik and so on up to In are component intervals. Component intervals of subdivision sigma. Component intervals of subdivision sigma. Lower integral is what? Integration from a bar to b f is equals to least upper bound of LF sigma. Least upper bound of LF sigma. Okay, this is the definition of lower integral. Okay, and least upper bound of LF sigma is always greater than or equal to LF sigma. Obviously, least upper bound of LF sigma is always greater than or equal to LF sigma. See here, upper integral is nothing but least upper bound of LF sigma. Therefore, what is the relation between upper integral and LF sigma? It is upper integral is greater than or equal to LF sigma. Okay. But what happened? Upper integral, that is integral from a bar to b f is greater than or equal to LF sigma is nothing but summation which is greater than or equal to summation k runs from 1 to n m f I k into mod I k. This is the definition of LF sigma. But MF I k but small mf I k is equals to what? Greatest lower bound of f of x such that x is belongs to I k. Okay. Now, again by hypothesis also seen. See here, also seen. So what happened? F of x is greater than or equal to 0 almost everywhere. For almost everywhere, I will write a dot e dot in closed interval AB. Okay. Therefore, f of x is greater than or equal to 0. That's why its greatest lower bound GLB of f of x, x belongs to Ik, is also greater than or equal to 0. Okay. Greatest lower bound of f of x. Therefore, small m f I k into mod I k is greater than or equal to 0. Actually, greatest lower bound of f of x is nothing but small m f I k, which is greater than or equal to 0. If I multiply by this mod I k, which is also greater than or equal to 0, suppose call this equation number 2. M of f I k into mod I k is greater than or equal to 0. That's why this summation is also greater than or equal to 0. So here we will get A bar to BF is greater than or equal to 0. Thus we have proved which we want to prove. Okay.